Good afternoon, everyone. Today we're going to do a video on finding the vertex of a quadratic function, namely this quadratic function, in 3 different ways, and a bonus 4th way using calculus and derivatives. So, to start things off, we have our function y is equal to x squared plus 2x minus 15, and a token graph to go along with it, so we can kind of visualize how we're going to find the vertex and where it's going to be. So, strategy number 1. We can always find the x-coordinate of the vertex by x is equal to negative b over 2a, okay? A being the x squared coefficient, b being the x coefficient. And so we can find the x coordinate of the vertex by x is equal to negative 2 over 2 times a is 1. There's nothing in front of x squared, so I'm going to apply that's 1. And so negative 2 over 2 times 1 means negative 2 over 2, which means negative 1. And so our vertex is going to be at, we've already found that the x coordinate would be negative 1. And to find the y coordinate, we can simply plug that back in to our equation for y. And so we'll have y is equal to negative 1 squared, just substituting negative 1 in for x, because x is equal to negative 1. And so negative 1 becomes x, so we have negative 1 squared plus 2 times negative 1 minus 15, giving us 1 minus 2 minus 15, which is negative 16. And so here's one way to find our vertex. This is most likely the first way that you learned how to find the vertex, okay? Our second way would be to complete the square. Completing the square is something that can be a little confusing at the start, but once you get the hang of it, it's not too terrible. And so if we want to complete the square, we're going to start by factoring just the first 2 numbers, and then we're going to turn it into a square, a full square of a binomial. And so what we're going to do is we're going to have y is equal to x plus, we're going to take half of the b value, so half of the x coefficient, which means half of 2, meaning 1, and so we'll have x plus 1, and we're just going to be looking at the first 2 terms of our function, and we're going to make it into a binomial that is raised to the power of 2. And then we still have minus 15 afterwards. Now what we have to be mindful of is that x plus 1 all squared, if we actually expand that, just this part, that's a horrible symbol, pardon me. If we did expand this back out, what we get is x squared plus 2x plus 1. Now that plus 1 is not found in here. We just created it out of thin air by wanting to write a binomial all squared. And so to balance it out, the plus 1 needs to be balanced out with a minus 1 afterwards, okay? And now that we've done that, this is called either writing the equation in transformational form, I'll jot that down, transformational form, or you might have heard it referenced as vertex form, okay? The reason why we call it that is because once we go ahead and simplify this, we have y is equal to x plus 1 all squared, negative 1 or minus 1 minus another 15 means minus 16. We actually get the coordinates of our vertex by flipping the sign on the x coordinate and keeping the sign on the y coordinate. And so if we flip the plus 1 inside the bracket, we get negative 1 in for x. And if we keep the negative 16 outside of the brackets, we get our y coordinate for our vertex. And so this is usually called vertex form because it readily gives us the coordinates of our vertex, okay? Our third strategy would be to note that any quadratic function is symmetrical about the vertex. And so we know that the vertex is at negative 1, negative 16. So I'm going to draw that negative 1, let's say negative 3, negative 6, negative 9, negative 12, negative 15. So we'll make it around here. And the point will be negative 1, negative 16. This will be our vertex. Now, we know that a quadratic is necessarily symmetrical about the vertex, okay? So that means that if we can find the 2 roots, its 2 zeros, its 2 x-intercepts, then we always know that the vertex is necessarily in the middle of our 2 zeros, necessarily so. And so if we go ahead and just factor our quadratic, which is probably something you've already been introduced to and practiced quite a bit, if we need the zeros of this function, then we know the vertex is smack dab in the middle. And so let's go ahead and factor that. We have y is equal to x squared plus 2x minus 15. And so we're looking for two numbers that add to make our b value, add to make positive 2, multiply by negative 15. So again, I'll write that down, add to make positive 2, and the same two numbers that multiply to make negative 15. You can look at the factors of 15, if that helps. Get your brain running. So we have 1 and 15, and we have 3 and we have 5. And that's about it. So the only candidates that really come to mind are going to be 3 and 5. We want a difference, we want a sum of positive 2, and we want a product of negative 15. And so one of them is necessarily going to have to be negative, and we want the sum of the two numbers to be positive 2. And so we'll have to go with negative 3 and positive 5 to have a sum of positive 2. And likewise, we can multiply negative 3 and positive 5 for a product of negative 15. And so since the x squared coefficient is 1, we don't have to use decomposition. We can go ahead and factor right away as x minus 3, bracket x plus 5. And we know that we're really solving this equation equal to 0 to find the roots, right? Roots are when y is equal to 0. And so we can replace y with 0 and solve. And we know that if 0 is going to be equal to a product of two binomials, then we either have the condition that our first binomial is equal to 0, or our second binomial is equal to 0. And if the first one is equal to 0, if x minus 3 is equal to 0, then we of course get x equal to 3. And if x plus 5 is equal to 0, then of course we get x equal to negative 5. And so these two are our two roots, our two x-intercepts. And so we'll plot one here at 3, 0, and we'll plot our other one at negative 5, 0. And so now we can use an average, or we can simply think what is the middle of positive 3 and negative 5 along the x-axis. So these are 8 units apart, and so 4 units would be in the middle, which would bring us right to negative 1, which is what we see when we use our two other strategies. And so once again, we see that the vertex is going to be smack dab in the middle at x equals negative 1. And so we can also get the average x coordinate of vertex. We can take the average of 3 and negative 5 to get the average of two numbers. We add them up and divide by 2. And so that's positive 3 plus negative 5 divided by 2. Positive 3 plus negative 5 is, of course, negative 2 divided by 2, which is negative 1. And so x means x is equal to negative 1. It's going to be the x coordinate of our vertex. And then once again, we could use our original function to get y. Plugging in negative 1 in for y would get us the y coordinate of 16. And we've already done that over here in step 1, and so I won't bother you with the details once again, but you see the idea. And then our bonus fourth strategy to find our vertex would be to look at our derivative, because our first derivative provides us with the slope of the tangent line to the function. And so if we graph this quadratic, this is going to be a positive quadratic with a vertex at negative 1, negative 16. Sorry, just had a second guess for a second. So if we go ahead and graph this, we're going to have something like that. That's a rough sketch of our function. We have our vertex down at the bottom, we have our two roots, and then we have a perfectly symmetrical function about the vertex, right? The vertex acts as our axis of symmetry, which is probably a term you've heard many times before. I'll just jot that down. Axis of symmetry. That's why we can make symmetry. That's why we can use this symmetry argument for number 3, arguing that our vertex is always in the very, very center of our two roots. And so, since our first derivative looks at the slope of the tangent line to the curve at any point along the curve, if we found the point where the slope of the tangent line is 0, this, a perfectly horizontal line, would have a slope of 0, then that would have to be a maximum or a minimum. And in the case of a quadratic, that will be our one and only vertex. And so if we can look for any zero of our derivative, namely if we call f of x squared plus 2x minus 15, then we're looking for any zeros of f prime of x. And if we go ahead and differentiate using our power rules, f prime of x would be 2x plus 2. And so if we solve for f prime of x equals to 0 to get the slope of 0 of the tangent line to the curve, which would indicate a critical point, a local min or local max, here our vertex for any quadratic function, then we look at f prime of x, prime of x, which is equal to 2x plus 2 equals 0. And so we can solve this fairly straightforward. If 2x plus 2 is equal to 0, we have 2x subtract 2 is equal to negative 2, and then dividing by 2 on both sides leaves us with the solution x is equal to negative 1, and of course we can plug that back in to find our coordinate in y for our vertex. And so once again, we would get negative 1 and negative 16 for our vertex. And so there are 4 different ways to find the vertex of a quadratic function, because I know these come up very often in physics problems and in kind of projectile motion problems and all sorts of different situations. And so you have 4 strategies now. I hope this was helpful to make some connections between the different techniques that we learned throughout high school with quadratics and with finding vertices. If you guys have any comments, suggestions, please let me know. Any future videos are always appreciated, and thanks for